Welcome to dsgn380. This is a simple, fairly straightforward video. We're just trying to show that bending is bad. We're mostly interested in this green shaft down here. This is the analysis view right now. You can see that there's quite a bit of gap between these members. And up here it's more symmetrical. It is symmetrical, but there's no gap anymore. We've replaced essentially one large pivot with a sort of an interleaving set of plates, or however you want to call it. We're just going to run this through the simulator to have a look at this. Notice down here we've got quite a bit of carry on going on. This is Colin making it and trying to figure out how to model it. This is strange. It's based on Orlov Volume 2 Figure 109 Art S. They're not shown this way. I've stacked them here. The goal here is to use one simple simulation and show the effect. I want the simulation to run smoothly, and I want the same load going through both joints. So why not have them sequential? We'll just stick these together in a way. So once you've got, probably post a file for you to download, probably step, go ahead and do the same thing. So go to Design, to Simulation, and you'll see I've already set this up a little bit. We've got a load here, so I won't go through all this stuff at our leisure. Let's finish the results. Do it again. So we've got a load case here. So we've got loads. This force is going both ways, two phases, and it's negative, meaning it's pulling, so pulling away from the face, and it is 1 times 10 to the 5 newtons, so 10 kilonewtons pulling through this, so that's fine. Now, force per entity, we've run into this problem before, so I'm actually going to fix this now that I'm thinking about it. Sorry, you're hearing me thinking. I'm going to change this load to 2 loads, so let's go for just the top. We'll put at 10 kilonewtons to see if that looks the right way. And we notice, yeah, it's pointing down, positive Z here. So let's go to negative 10 kilonewtons. Okay. Let's add another load here at the opposite end, 10 kilonewtons. And you'll notice it's pointing the wrong way, so negative again. Perfect. Now, we don't have any fixed geometry here yet, so let's see what I've done. There's a frictionless. So what I'm doing here is trying to stop it sliding around, and all I've done is friction held the 2 outside fillet corners of this guy. This will stop it moving. Also, well, it'll stop it moving in the XY plane. We also want to make sure that under Manage, we have Remove Rigid Body Modes turned on. This will stop the calculations which are always slightly off because of truncation and rounding errors. The 16th or whatever decimal place. If it keeps an eye on it and makes sure it doesn't move too much. This will stop it getting carried away. See here, everything else looks fine. What about contacts? We should expect to see quite a lot here. I've added one manually. I've stuck these 2 together. So they're 2 separate components, and just use a bonded. I mean, you can see manual for that. To add a manual contact, you're under contacts, manual contact. Again, back to manage contacts. I went through and added them all automatically, and then made some of them rough. So this will kind of stick it in, but will allow a little bit of sort of separation. So it's not a bonded like there are in between one here. Got separation for the other sides, so where it's allowed to move. So have a look at those in slow-mo, see what's going on, but we'll leave it at that. Next, you can see here we've got a warning because I've got out-of-date results. Let's have a look at the mesh. Quite a dense mesh, and interested in parts close to where the flow lines would be quite jumbled or tight. tight, curved, bent, all that sort of stuff. So let's have a look at the settings. Quite high, 10%, but under advanced settings, 10. So we've got here 30 degrees on maximum turn on angles. We've got a 1.5 on maximum adjacent mesh ratio, and maximum aspect ratio is 10. Minimum element size 20. Say okay to that. Looks like we're ready to go. Let's see what the pre-check says. So it may not be completely controlled. This is okay. Let's have a look at degree of freedom view. Potentially fixed. This is why we turned on the old remove rigid body modes. We have balanced loads. So one force is 10 kilonewtons. The other one is 10 kilonewtons in the opposite directions, pulling away. So we expect a tension load across all of these joints. Let's try running it. Make sure you're seeing education. And off we go. And we're back. Now this is deformation magnified or exaggerated. Let's have a look at our results here. See, the maximum stress is, the whole thing's not in quite a, it's actually in quite a bit of stress, but you can see here, see what we expect to see, kind of all in tension, so about the same all the way through. With the high points where, right? So no surprise really in this shaft, which is being bent because of the gap. So if we look at von Mies, even more obvious. So our low stress. Now we would expect to start seeing that typical bending effect. Depending on where we look, you see high stress at both sides. So let's hide this model component. So this one is, oh, it doesn't highlight. Let's find it. That's the one it's kind of getting in the way. Into the typical bending behavior here. And some bending also in these, the fork almost coming up, where it's being bent out by the shift of the shaft. So this is all kind of bad. What do we see in these other guys? Yeah, a little bit of stress around the end where it's thinned out, so no surprise there either. Flow line wise, it's what we kind of expect to see. Up here, do we see any bending? So far not. Let's try hiding everything but the shaft, which we might see some bending in. Let's see if we develop any typical bending, a little bit side to side, but it's all on one side. So this is more just, looks like tension or compression, crushing or stretching. So what is it? Let's see. Load's pulling up. It's crushing from these two forks in the middle here. So it's trying to bend, but it's been resisted. So we've removed the bending here. Nice job, and ended up with quite a bit less stress in the top. But the easy way to see this is all the same material. Let's have a look at the safety factor. Minimum 7, so not a bad balance. So no surprise there. It's not really telling as much. Sorry, this isn't minimum. Minimum is 7. It's a bit overbuilt. Sorry. Probably looking here at displacement, tell us something. Now, because it's all lined up, it's not going to tell us too much because we're going to see shifts magnified by later shifts. Let's have a look instead at just one particular displacement. So instead of total, let's look at, say, X. So you can see here that this is moving quite a bit. This guy. Now if we want to isolate that. Oh, wrong one. And, you know, for example, we might be interested in the shaft on the other side. That's that one. So we can see the displacement here. You can look at it like this, but you can also just rotate around a bit. See our max, it's not displacing too much. This is, again, exaggerated. Actual is going to look the same as the real. But we can see here it's bending quite a bit. Again, just looking at these two guys, stress. If we just look at the shafts, or the pins, we can see as we remove or stop looking at the low stress material, we lose the top one more or less completely before we lose the bottom one. So this one's in quite a bit more stress because of the bending. Keep in mind they're both experiencing the same load both directions. So this is arguably our FEA proof of bending is bad. There we go. So look at the whole thing again. Show it all. And there we go. Safety factor is uniformly okay. Displacement is, as we show, highest left to right, but totals, reaction forces. We should see that in our what am I looking for here? In our constraints. Strain is related to stress, so we'd expect to see more down here in the more bent, higher stress area. Contact pressure and all the rest of it. So there we go. That's how we can kind of visualize why bending is bad. Over to you.